Welcome to this pre-recording of lecture 37. In computational geometry, there is an overlap with computer graphics. Today we look into a computer graphics problem, and we will define a binary space partition tree. The binary space partition tree generalizes the KD tree we have covered earlier in the course. In Segal, there is the boxing axis aligned boxes tree. That is also a connection that we will make in the end. And in some sense, computational geometry is also a second data structures course. So where we are storing geometrical objects. Okay, what is the project? What is the problem that motivates binary space partitions? That is the hidden surface removal problem. So we want to render a scene, so you can think about a flight simulator. You want to make it as realistic as possible, so what is seen in the windows should be rendered. So we have a viewpoint and a set of objects. We want to determine the list of visible objects. And we want to do this fast, actually very fast. We want to do this in real time. When you think about a flight simulator, the landscape probably might not be so in detail, but at least the landing strip should actually be as accurate as necessary to train future pilots. So the distinction between what is visible and not, we are removing what is not visible, and that is called the hidden surface removal in rendering a scene, a problem in computer graphics. Okay, what's the approach that we will take? That's the painter's algorithm. So if you paint, then you first paint the farthest objects. Perhaps you could start with the sky, and then you paint things over it. So you overlay the painting with the objects that are closer. So here from left to right, we started with the blue sky. In computational geometry, everything is a triangle. Then we have the green grass, and then we have the red house. So this is the cartoonish version of the painter's algorithm. Okay, so that works, except that sometimes you don't know what to paint first. So let's look at the picture here. So we start with the blue sky, then the green grass, and then the red house. But actually, except that the red triangle here is below the blue triangle. Well, why don't you then start with the blue triangle? Well, you don't start with the blue triangle, so start with the green grass. You paint over the red house, but then you have to paint the sky, the blue triangle, and that should be hidden. So that's again a problem. You can repeat this for the red. Okay, so with the cyclic overlaps, you can't really decide which object is farthest, which is closest. So the problem is simply undefined. So certainly not well defined. So in some sense, the hidden surface removal, if we have to decide which object is close to us, which is farther to us, that's something that for cyclic overlaps you can't decide. What's the solution? Well, the solution consists in fragmenting the objects. So here for this particular cyclic overlap example, the red triangle is now fragmented in a yellow triangle and a red quadrilateral. So you see that the yellow can be painted first, then we can do the blue, then the green, then the red. And that actually resolves the problem that we have with deciding which should be removed, which object should be painted first and which object should be painted later. So problem solved. So the painter's algorithm is actually a good algorithm if we fragment the objects that we want to paint. What we need and what we will propose is a data structure to store those fragmented objects. We need to be able to retrieve those objects quickly. So in a way, storing them in a binary search tree will be an obvious choice. Okay, we look at triangles in the plane for objects. In general, we look at convex polytopes, and or we look at any objects that are approximated by convex polytopes. So the triangles that we see here are the facets in tree space. But for the simplicity of the drawings, we have 4 triangles in the plane. For objects that we want to store in a data structure so we can uh, then quickly decide the visibility. Okay, how shall we do this? We do divide and conquer. We pick a line, L1 here, and we split the objects. One object O1 is above the line, the other object O2 is partially, so we have fragmented O2. O2 is split in a way in a triangle and a quadrilateral. Um, and the O3 and O4, so the third and the fourth object, they are at the other side. So we can split more, so we can then separate the first object from the second object. So the second line is actually not a line, it's a half line. So it only applies to one half of the plane, the half that was splitted by the first line. We also split the second half that separates the fourth object from the fragment of the second object and cuts the third object. Okay, so then we have one more split here in this example where we have now a line segment between that takes an extra partition. Okay, and I said the last one. Here is the last one. So now every object is actually in its own space. So we had 4 objects, we have 5 lines, and we typically will have more lines to isolate every object because of the fragmentation. So this is a picture in the plane. In space, we are using planes to separate the facets of the polytopes. So in some sense, the fragmentation of a polytope is a different problem that we actually will not address here. So in the remaining part of the course, we are in lecture 37, in the remaining part of the course, we will just dabble into some of the remaining chapters. So, but I hope you get the idea. So we have partitioned objects. with splits. So the splits naturally define a tree. It's a splitting tree. All the fragments are in the leaves. So here you could see this a little bit as, so the picture is not accurate. So one of the exercises is actually to um, correct it, because you see that the second object, what is here labeled as O2, appears twice. What it actually means is that in this leaf here we have the triangle, and in the other leaf we have the quadrilateral. The same thing for the third object. But I guess you get the idea. So when we have a linear equation that represents the line, or in general, we always have a linear equation for a plane. It also works in any dimension, so you can define it in n variables. Then we work with hyperplanes. We have one equation equal to 0, and then we can distinguish for any point whether the value of that linear form is negative or positive. By convention, the left child stores the negative half, and the right child stores the positive half of the plane. Geometrically, you could think about the orientation of a line, where you walk from the line. You have a left side and you have a right side, whether you go in the line, in the orientation of the line. So you could define a line as a point at the extreme bounding box, and then you have a vector, whether you then lie to the left of the vector or to the right of the vector. This is for lines, by the way. I'm now must a little bit think about with a plane in 3 space, you will have a vector that is normal. And you could also orient your planes with regard to this normal vector. So the vector interpretation of this is that you have C1 and C2, which are the coordinates of the vector. And then you have your point, so you have your inner product. And depending on whether the inner product with any point with the coordinates of your normal vector, whether that makes is this larger or less than the right hand side. So there is a vector interpretation of this as well. Okay, here is the formal definition, generalized to 3 space, without drawings. So we have a plane represented by a linear form, 4 coefficients. And the linear form can be seen as a function, so you can evaluate any point in the set. So the set is the entire, S is the entire 3 space. We have the negative half plane, the plane, and the positive half plane. So these are the 3 sets. So it is properly a partition. So any point belongs to any of these 3. So what is then the binary space partition tree, or BSP tree? At the leaves, either it is a leaf, if there's only one element in the set. So now we look at a set of a finite collection. So if there's only one element, then it's just that one element at the leaf. That's then also the root of the tree. Otherwise, we have a random hyperplane that we can generate as we go, and we store at a node all the points that lie in that random hyperplane, At the left side, we store the negative half. So when you evaluate the random hyperplane at any object, any element of your set, then it is at the left side if it evaluates negatively. Otherwise, it is placed at the right. So this is a partitioning. So, and that works for any um, set of elements. It's easiest to see for points, but you can also partition line segments in that way. Or in general, we are partitioning polytopes, where the polytopes are defined by the vertices, the facets, and the line segments. Okay, let's think about line segments, and also let's think about the size of this binary space partition tree. Before we think about algorithms, we always must consider the complexity of what we are computing. So we will also use this binary space partition for searching, for navigating through this data set. So it should be obvious, the more that we fragment, the largest the size will be. So in some sense, in the worst possible case, you kind of are cutting with your plane through every object. And even the fragmentation process, if you think about having to fragment polytopes, you will have to cut through all the facets and all the line segments that are the edges of the facets that you are cutting. Okay, let's look first at a simpler problem. So building a binary space partition tree for a point collection is rather straightforward, except that where to choose your splits. You would also like to have a balanced search tree, although one can always rebalance a tree. Okay, so as far as line segments goes, there is an auto partition. So if you have line segments, you could take as a split one of the line segments. You could take one of the line segments to define your splitting line. So if you do that, you could think about picking somewhere the middle segment. So if you think too much about this, it's gonna cost you linear time, but it should be, or perhaps it should be clear after you have done the exercise. Work on an example, draw some line segments, and then there might be an obvious segment to pick. So, but each time, if you actually do this with an auto partition, you will always pick a line segment. And at some point, you will run out of line segments. So if you cut your line segments neatly in half each time, it's clear that you can only pick n line segments. So it is linear. Uh, so your binary space partition tree, the auto partition should actually always give you a linear size. The book actually gives an explicit bound, so you can be quite precise for the constant as well. If you think about an auto partition for three-dimensional objects, well, we have typically facets. You can think of an auto partition as a plane that runs entirely through a facet. It's kind of, you pick one facet of the object that you see, and you start to partition your objects running with planes running through the facets. So the auto partition is kind of the obvious choice to take, because then you have less fragmentation if you take your planes through a facet or through a line segment in the plane. Okay, here is then the construction of a binary space partition tree. So we have a set of triangles. So the triangles are facets. So even if you have, say, a cube where all the facets are squares, then you can still triangulate this. We see that we have seen that Seagal does this automatically, so that you always end up with triangles. So we have actually here an auto partition. So we define a plane so it passes through some triangle. Then actually you have at least one of the triangles that is in the plane. So you have at the node represented by the plane, you have at least one triangle sitting in there. We have the negative half space and we have the positive half space. So the quadrilaterals in these negative and positive half spaces need to be triangulated. So I indicated earlier that the picture on slide 15 was a good picture to start with, but actually not entirely accurate. So these quadrilaterals, so the leaves, are actually storing disjoint objects. So the P in the BSP is really important. It is a partition. A partition means that the intersection of the objects in different sets is empty. And also partition means that the union, if you assemble everything again, you have the entire collection of objects. So in your hidden surface removal problem, you shouldn't really forget anything. So you should really show everything that's there, except some things that are hidden from view, but they are still there in your data structure. Okay, here is then the algorithm. So it's a recursive, we had a recursive definition. Now also we have a recursive algorithm. If there's only one element or even less, then we don't really do anything. We construct a leaf. We return the tree, there's only one node. Otherwise, we do this auto partitioning. We take the plane through the first triangle. Why the first? Well, it might be good to randomize. So that's another issue that we have encountered many times in this course already. We could be unlucky in picking the first triangle. How could we be unlucky? Well, it could be that this first triangle is in such a position that the plane causes a lot of fragmentation. So it's actually often good to take somehow, you shouldn't put the first triangle somewhere very far away or very close, but you should kind of have a good partition without too much fragmentation. We have then the obvious steps. So here I had many instructions on the same line in 4 and 5 just to make the slide, everything fit on the slide. But you see that the algorithm is fairly straightforward, even though the problem can be quite complicated, especially on the choice of the planes. Okay, so what are now special cases? So you might have facets that are not triangles. One can say that, for example, everything could lie in the same plane. So in some sense, then you don't really have a tree. So in some sense, the algorithm looked quite straightforward, but there is actually the special case when you would have a lot of flat areas. So in some sense, what this could mean is that your point of view is also kind of very special, if you would, but we are not there yet. Okay, so we have all the triangles lying in the same plane. Then what is proposed here is that just like if we would have this with the convex hull, we would go to the two-dimensional convex hull problem, um, as we mentioned in the previous chapter. Now we go one dimension less. So again saying that if every triangle lies in the same plane, then we don't have a tree. We may have a tree if we are going to work with splitting lines. Now, question, is there a special case? Could it still go wrong there? And yes, indeed. If everything lies in the plane, then it could be that everything is collinear. Everything lies in the same line. So in some sense, your two-dimensional convex hull collapses into one line segment. And that's then a special case. So also that special case can be then dealt with recursively. Then what you're doing is you're storing different line segments that then need to be partitioned. And then you have a partition of points, again, all points on the same line, which can then be quite straightforward, be dealt with sorting. This is always why we have the n-log n cost sitting in there. Okay, so that was why this algorithm was quite straightforward. Another way to look at this is that the set of triangles is in general position. So there's nothing special about them. This algorithm is then good enough. Okay, we are more than halfway. What do we do with this now? Well, let's think about our original problem here again. We want to solve the hidden surface removal problem. And that's with the painter's algorithm. So here a cartoonish picture again. So we have one eye at the left, and we look at this scene. So the eye is positioned in one sector of the plane. So we can decide where we are in this tree with the splitting lines. We can here decide we are at the left of L1 to the right of L2. What then means the farthest? Well, here is where the painter's algorithm will work. If the viewpoint is here to the left, then we will first have to paint everything to the right. Everything to the right is splitted first with this L3. We have everything also to the right of L3, everything to the left of L3. Even though L3 is a line segment, it can be considered as extending. So for the objects that are inside or outside, left or right, we can still decide where the position of the viewpoint is with respect to the objects in the tree. So in the painter's algorithm, we're going to go for the objects that are first farthest from the viewpoint. We go to the child, the objects in the child, stored in the child that are farthest. Then we do the objects, we paint the objects in the node, and then we do what is to the left. So it's a tree traversal, where we traverse with respect to the viewpoint. Here is described in words, and you could view this as a very high-level description of the painter's algorithm. The painter paints the farthest objects first. So the traversal of the binary space partition tree visits all nodes at the other half plane as the viewpoint. So we have one half plane where we visit everything there first, then we visit the object stored at the node, and then everything at the same half space at the viewpoint. So it's now a classical recursive tree traversal algorithm. And this brings us back to the conventional algorithms of data structures. It's a recursive algorithm. If we are at a leaf, we visit all the fragments there, so we paint all the fragments. Otherwise, for every hyperplane, we can decide in which viewpoint, where the viewpoint is. And if the viewpoint is in the positive half, then we will first visit everything in the left half, because the left half stores everything that is opposite from the positive half. So in visiting all the nodes, we need to pass the viewpoint. Even though the viewpoint was not there when we constructed the binary space partition tree, we can use the half planes to very quickly decide whether the viewpoint belongs to the left or the right child. So there is this branch of the algorithm, and then there is the symmetric branch when the viewpoint lies in the negative half space. Then we visit first everything in the positive half, stored in the right child. Then it should be a shame to forget the case when the viewpoint lies in the half plane, and then actually I think we have here a choice. We can visit everything that is at the right child or the left child. So the special case here might still matter when all the points are in the plane. So there might still be um, subdivisions here. So that's why here you still have the right child and the left child. Um, and there might have been here the special case. It could have been that if there was just one triangle there, it could have been stored at the node. Um, so in some sense, this algorithm is a high-level algorithm. If you were to implement this in detail, you may encounter some of the special cases. So the special cases we can deal with hand-wavingly here in this description. If it comes to an actual implementation, one might need to be a little bit more careful. Okay, we are almost there. So perhaps I've moved too fast. We are somehow summarizing one entire chapter in the textbook. There is a possibility in this course to do a final project. When I did a Google search on binary space partition trees and AABB trees, they were covered in one lecture in computer graphics. So that's why that's my next slide here. Here is another exercise. Why is now randomization necessary? Well, this is to avoid the worst possible case what you may have with fragmentation. So you could have an unlucky choice of a fragment. So you have given not a fragment, so you do have triangles given. You could have an unlucky choice. Well, that is the case whenever a thing lies in the plane, but you could have many triangles that are lying in the same plane. So you could have a polytope that has a face that have many vertices. That's another way to see this. Um, so then actually using that plane will actually um, cause problems. So what I'm actually saying here is that there is an exercise. Find actually a worst possible case. And you can see that these worst possible cases are going to occur where the inputs are kind of high density. So you have many triangles that are all very closely related to each other. So you can think of a constellation of polytopes that are all in line. And you kind of you have the biggest polytope at the end, the next polytope, then the next polytope, kind of a sequence of polytopes. You see them all, but if your fragmentation is actually not very good, um, instead of cleanly cutting them, dividing them in the line of view, you actually cut along the line of viewpoint. So I'm now improvising a little bit, but you can see from the natural way how vision goes. You have your viewpoint and then the direction in which you view, and it might be very convenient to actually to cut parallel um, in your common viewpoint. Again, if you design a flight simulator, the most important object is actually your runway, and it might be convenient to partition perpendicular to the orientation of the runway. Okay, here is the theorem, which is the main result of this chapter, something that we don't prove. Again, if you are more mathematically oriented, this would kind of um, render you kind of uneasy. Um, the n square has to do with the fragmentation. So in some sense, you could have a very unlucky choice of lines where you continue to somehow fragment almost everything. So in the very unlucky case, you would keep on making just as many new fragments as you have already, and you would only split off one triangle each day with an auto partition. So that is here actually the answer for the unlucky case. So you have your auto partition where you take away one triangle, but then you cut all the other triangles. So you're left with n minus 1 other triangles, and you continue that way. So that creates an n square size. So there is always such a choice. There is such an unlucky inputs. But that will most likely only happen if everything is very dense. Otherwise, you could think of an n log n. In the better case, you have a divide and conquer. So your auto partition works perfectly fine. Okay, quadratic time algorithms. Doing this in real time is still possible, but it will impose a severe limit on the number of objects that you can consider. Okay, um, last part. We have spent considerable time on orthogonal range queries, where we actually split a data set using half planes that are either horizontal or vertical. These are actually quite natural, also quite economical to consider, where your half planes, they're just stored by constants. And you have to um, maintain also the coordinates. So very sparse representations, very convenient. Also, most likely natural if you are storing data that is not directly correlated to each other in a database. If you store a geometric scene where polytopes can represent more coherent information, that might not be desirable. If we do a cost analysis, we have the worst case, but then also we have the best case for the low density inputs, but it might also be most useful to do an average cost analysis, something that we have done here. We have not done here. Okay, so we have encountered already AABB trees, and the reason why that was because we looked into the Seagal Swig Python bindings. And there, one of the very first examples was actually the axis aligned bounding box. And that's the, uh, if you are interested more into computer graphics, you could see that this is good for objects that are kind of skew. So you can kind of take into account the orientation of the objects. So the AABB tree is a very convenient data structures in computer graphics. Okay, this is a very quick summary of one entire chapter, chapter 12 in our textbook. In some sense, in this course, we only have 15 weeks, so I had to make a choice either to go very carefully through a part of the course, and we've done this. We covered the first 11 chapters rather carefully. But then that means that we still have 5 chapters left. We will cover 4 of them. This is the chapter on binary space partition trees and other geometric data structures that generalizes the KD tree.